Turbofan engine. Around 1970, rising fuel prices made the pure turbojet engine an unattractive propulsion system due to its high specific fuel consumption. So, this made a new breakthrough in gas turbine engine industry. We call it turbofan, which apply at most modern aircraft nowadays. A turbofan engine has a large fan at the front, which pressurizes a large volume of air, part of which bypasses around the engine core, which is turbojet, which this significantly improving the specific fuel consumption.
7B is a high bypass ratio engine. The primary flow passes through the combustor, while the secondary flow passes only through the fan. 80% of the engine airflow, accelerated by the fan, is directed into the bypass duct and provides 80% of the engine's thrust.
The objective is to increase the thrust without increasing the fuel consumption. It achieves this by increasing the total air mass flow while not having to burn fuel to heat the bypass air in the combustion chamber. Due to this, there is a special term that only being used in turbofan called bypass ratio. Bypass ratio, or BPR, is defined as the ratio of the mass flow rate of cold air through the bypass duct over mass flow rate of hot air through the engine core. There is two types of turbofan engine. First, we call it non-mixing bypass turbofan engine. Second one, we call it mixing bypass turbofan engine.
Non-mixing bypass turbofan engine.
Non-mixing bypass turbofan engine is a cold bypass air exhaust out of the separate nozzle than the core hot exhaust gases. As you can see here, this is a typical schematic diagram for non-mixing bypass turbofan engine and also TS diagram. We label each station from 0 to 9 in order to easy us to calculate the performance of each component. Process 0 to 1 takes place at the intake. Process 1 to 2 is a process at the low pressure compressor or fan. Process 2 to 3 is a process of high pressure compressor, HPC. Process 3 to 4 is a process at the combustion chamber. Process 4 to 5 is a process of high pressure turbine. Process 5 to 6 is a process at the low pressure turbine. And then process 6 to 7 process at jet pipe. And process 7 to 8 a process at the exhaust nozzle. And then the level 9 actually is a process at the bypass. The fan, or low pressure compressor, LPC, is generally driven by the low pressure turbine, LPT, assuming that there are no other devices powered by the low pressure turbine. The law of conservation of energy will give that the work required by the low pressure compressor will be equal that the work that produced by the low pressure turbine. The work for low pressure compressor can be calculated between the temperature of T total 2 minus T total 1, and then the work for low pressure turbine, it can be calculated between the temperature of T total 5 minus T total 6. Please pay attention that the mass flow rate for the cold section, which is at the compressor, is the additional combination between the mass flow rate from the bypass and mass flow rate from the air. While at the hot section, which is at turbine, the mass flow rate is combination between the mass flow of air plus mass flow of fuel. The high pressure compressor, HPC, is generally driven by the high pressure turbine, HPT. That means the work required by high pressure compressor will be equal to the work high pressure turbine produced.
Mixing bypass turbofan engine.
For a mixing bypass turbofan engine, coal bypass is mixed with the core hot gases and then exhausted out the same nozzle. This quite differ with a non-mixing bypass turbofan engine. As you can see now, it's a typical schematic diagram for mixing bypass turbofan engine. Like non-mixing bypass turbofan engine, we label each component with the section number. Section 0 to 1 is a process at the intake. Process 1 to 2 is a process at the fan or low pressure compressor. Process 2 to 3 is a process at high pressure compressor. Process 3 to 4 is a process at combustion chamber. Process 4 to 5 is a process at the high pressure turbine. Process from 5 to 6 is a process at the low pressure turbine. And then, this is a significant difference with non-mixing bypass turbofan engine, which is the process at 6 to 7. This process, we call it the process at the mixing chamber. Process 7 to 8 is process at the jet pipe. And lastly, process 8 to 9 occurred at the nozzle, similar like turbofan, non-mixing turbofan engine. As you can see also now, it's a TS diagram for each process. For a mixing bypass turbofan, cold air from the bypass flow and hot air from the turbine is combined in the mixing chamber. There will be some losses in total pressure on mixing. Therefore, the mixture values of constant pressure specific heat, gas constant, and the ratio of the specific heat can be determined from an enthalpy balance of these two streams. The subscribed mix represent the properties of the mixed streams. All these values can be determined by the following relation. Besides, the mixing process is adiabatic. Therefore, applying the conservation of energy will give that the work